So it's my pleasure to introduce Dr. Gurtej Kanwar. He's from University of Bern. He's doing his postdoc there. So before that, he did his master's and PhD work at MIT. So recently he's doing very interesting work in machine learning related to lattice field theory and in general machine learning. So we invited him to give a talk. So what's he's doing. And so today he will be speaking on the machine learning for lattice field theory. So Gurtej, please go ahead.
Okay, thank you so much for the introduction, Ilmani, and the invitation as well. I appreciate the opportunity to be able to speak, and hopefully today we'll give a bit of an overview of the work that I've been doing, sort of wrapped up during my PhD, but with some ongoing tendrils into the future on applying machine learning to lattice field theory, but also generally this idea of thinking about, well, in physics, how can we use, and especially in physics theory, how can we use machine learning in a controlled way where we don't sacrifice any of the guarantees that we have through other methods. So the story sort of begins with the motivations, with this state of the art, I guess, or state of the world situation we have, where we have a beautiful standard model. It's a story of many spectacular successes in that it unifies sort of all physical phenomena we see, at least in our human scales, in terms of the language of a quantum field theory that contains only 3 fundamental forces and only 19 free parameters. And with the discovery of the Higgs in 2012, it essentially was completed in some sense and provides many precise and accurately observed predictions in the space of cross sections, for example, E plus E minus dihadrons over a wide range of center of mass energy, or for example, the structure of resonances in hadronic states, which have been very accurately reproduced in recent times using lattice QCD, which I hope to say some more about just now. But of course, the standard model we know to be incomplete. And so there's many unanswered questions like, what is the nature of dark matter, whether particle or otherwise? And if it's particle, what is the structure of the quantum field theory extensions that we should use to describe it? For example, we also know that neutrinos have masses, which is unaccounted for in the standard model. And there's several ways that those masses could be included as kind of minimal extensions to the standard model, but it's important to understand which of those is the case and what the parameters exactly are by performing some measurements. And finally, there's this well-known problem of the matter-antimatter asymmetry, or early genesis of matter in the universe in the right quantities, which currently is not fully explained. So many of these questions, of course, immediately tell us that the standard model is incomplete, and we should ask how to extend it. But in order to actually make those extensions quantitatively and precisely, we need essentially a joint effort between theoretical and experimental work. And of course, the theoretical work is to provide an understanding of the measurements we make in a variety of experiments. So for example, in this top row here is just depicted a variety of sort of frontier experiments, I would say. For example, the Large Hadron Collider, which produces a variety of physical measurements in the various detectors. Up-and-coming Dune will tell us quite a lot about neutrino properties. The already running Super K does tell us already quite a lot about neutrino properties. And there's many, many more. Obviously, I've listed just 3 particular experiments. But to actually interpret the results of these, of course, we need to know what does the standard model say should happen. And if we have some candidate models for extensions to the standard model, we should also be able to predict precisely and quantitatively what they say the modifications to these measurements should be, so that pieced together, we can constrain the parameters of those beyond the standard model extensions. Now, just to name one example, we've had some recent exciting results in the space of the measurements of the muon anomalous magnetic moment, or the muon G-2. And this is really a beautiful kind of collaborative effort between theoretical and experimental work that requires further improvements on both sides in order to make this, this tension an actual discovery. But the state of the art right now is, at least as of last year, Fermilab published an updated result of the measurement of this anomalous magnetic moment, which confirmed previous measurements from Brookhaven, and altogether the experimental average on this plot sits in this range. And on the other hand, we can also predict this quantity very precisely, of course, from the standard model. And this involves QED calculations to very high order, electroweak corrections, and a large number of hadronic pieces, in particular, the hadronic vacuum polarization at several orders and the hadronic light by light scattering. So this is a 4-photon interaction with hadronic blob in the center. And these require some accounting for the strong force, which as a theory or quantum field theory with strong couplings at the energy ranges required involves fundamentally non-perturbative theoretical techniques, some of which may be ab initio, for example, the use of the lattice, which directly goes from our theory of the strong force, QCD, to these predictions. And some of these are based on data-driven theoretical methods. And here data, I mean experimental data-driven. So combining existing experimental results with, for example, dispersive or analyticity-based approaches to derive these quantities somewhat indirectly, but with different statistics and systematic errors associated with that. And altogether, one can see that the standard model prediction has a discrepancy with the experimental average, as is well known, of course, to this audience. But one can also look at the error bar contributions to the standard model prediction and see it's really the hadronic pieces, the vacuum polarization and light by light, that dominate that error budget. And so as this Fermilab experiment continues to drive the experimental error down, we as theorists should be focusing on trying to drive the standard model prediction errors down, and that essentially has to come from the hadronic pieces. Now, a second motivating example is the tensions also observed in B meson decays at the LHC, as well as in Bell and Babar. And just to post one sort of summary statistic of this, it has been observed in the ratios of B meson decays via semi-leptonic processes, including either a tau or a light lepton, a muon or an electron, that these ratios deviate somewhat from the standard model prediction. So just to cut through all the mess of this plot, essentially there's a small standard model prediction here on this two-dimensional plane of observables, and the experimental average as of summer 2018 at least lived about 3 to 4 sigma away from it. Now there's many other observables in this space, and the standard model prediction is not always as precise in, for example, angular observables with angular dependence and other sort of more precise and I should say maybe more direct observables that don't necessarily have ratios that cancel out hadronic uncertainties. And so there is still room for theory to play a role in understanding these discrepancies, even as the experimental results work to become more and more precise in this area. So altogether, we know that there is new physics to be found, and often these searches have significant theoretical uncertainties that originate from the strong force effects. And strong coupling requires non-perturbative approaches. And this motivates, I guess, my particular interest in this direction, which is to work with lattice quantum field theory, which is fundamentally a non-perturbative approach in that it involves a discretization on a space-time lattice. So this would be, for example, a 3D slice of what is actually a 4-dimensional lattice in a standard simulation, with some lattice spacing A that acts as a cutoff for UV divergences. And that's in contrast to perturbative Feynman diagram, for example, based approaches, where the UV divergences are regulated via other regulators, for example, like DIMREG or polyvelars or so on. And in the non-perturbative case, because this discretization is the regulator, the goal is to eventually extrapolate it away to zero, much like how one would take dim reg epsilon to zero at the end of the calculation. But of course, at the intermediate stages where this lattice spacing is finite, we need a way to actually make the calculation with a finite regulator, and that typically is performed numerically. So to give that formulation a bit more precise footing, and especially to get the notation straight for lattice gauge theories, which is particularly interesting because QCD itself is, of course, a non-abelian gauge theory consisting of gauge group SU3. These sorts of theories can be expressed, again, in terms of a lattice discretization, but keeping in mind that the gauge field ends up discretized on links of this lattice, whereas the other matter fields just get discretized on the sites of the lattice. But regardless of those details, at the end of the day, for a given discretization, one can essentially just prescribe a path integral definition for any given observable by saying the vacuum expectation value is in this regulator, the path integral over all of these dynamical fields degrees of freedom that live, say, on the links or on the sites, but a finite number of them. So therefore, this is a well-defined finite integration space over the observable times this e to the minus action factor. And the reason it's e to the minus action, not e to the I action, is because typically in these cases, one works with a Wick rotated field theory where we've moved to Euclidean spacetime by rotating time to I times tau. And this is just a detail to make the calculation more straightforward. And the idea eventually being that one can relate observables in Euclidean spacetime to things of interest in Minkowski spacetime as well. And of course, the action S here is referring to a discretized action. So it's something in terms of these discretized link and site degrees of freedom rather than a continuous field as it would be. But for sufficiently well-formulated actions, universality tells us that as we take the lattice spacing to zero, we recover the universal continuum field theory that we're looking for as long as we tune a few relevant parameters appropriately. So this path integral is now well-defined with a regulator. It's just an integration over a finite set of degrees of freedom. But of course, it's still a high-dimensional integral. And so one needs to use specialized techniques to evaluate it. And the standard approach is based on Markov chain Monte Carlo. So keeping in mind that this is the quantity that we are seeking to evaluate in essentially all lattice QFT calculations, the one-sentence summary essentially of Markov chain Monte Carlo is we sample a set of configurations. So this is values of the field on the whole lattice at once from this distribution, e to the minus action, normalized by this partition function z. And if we do this appropriately, then the expectation value, the quantum expectation value of O, can be estimated by the statistical expectation value of O on these samples. To actually do this sampling typically requires this Markov chain aspect to the Monte Carlo. And that means starting with some configuration, stochastically updating it repeatedly according to some process that equilibrates to a field sampled from the distribution that we are interested in. And so for sufficiently many updates here, you form, say, a very long Markov chain and just take some samples out of this to form an ensemble on which we can measure. And that ensemble should be distributed very nearly as this distribution that we're interested in. Now that's how we would generate, say, the actual field configurations. To extract physics at the end of the day, it's worthwhile to keep in mind that the quantities that we're usually interested in here are imaginary time correlation functions. So I mentioned when we're in this Euclidean metric or imaginary time, we would like to write down some observables that inform us of the physics. And these imaginary time correlation functions are sort of the first order thing that one could write down. So generically, the structure looks like an operator at imaginary time 0 creating a state and an operator annihilating the state with the same quantum numbers at imaginary time t. And for a well-defined theory, this can be spectrally decomposed. So it turns into a sum over exponentially decaying components where these exponents are just the possible energy states associated with the quantum numbers that were created and annihilated here by this operator. And one can just see from this spectral decomposition that if we take T much larger than the gap from E naught, assuming that's the smallest energy, to the next excited state, then this really gives access to the ground state energy, which, for example, if we're talking about a QFT, might be the mass of some particle or resonance. Of course, more complicated things can be done. We can access matrix elements, form factors, and so on by investigating more complicated operators. But this is sort of a sufficient view of what we care to do and will be sufficient to highlight the problems and solutions that I touch upon shortly. So speaking of problems, not all is well in the world of lattice. There's all sorts of obstructions essentially to efficiently producing these results, and that efficiency is required to essentially have small enough error bars to be useful in theoretical calculations. So the first problem is what is known as critical slowing down, and has to do with this sampling step. So this Markov chain Monte Carlo that's typically used to produce an ensemble of field configurations. And the problem essentially arises from the fact that most Markov chains are analogous to diffusive processes, in that stochastic update mixes and updates field variables based on their neighbors, but not necessarily based arbitrarily globally on the field. And so for growing correlation length on the lattice, as A is taken to 0, this Markov chain process tends to have longer and longer correlation time. So it requires many more Markov chain updates before you get an independent configuration from your chain that has no correlation with the previous one. And it's also the case, because these diffusive updates tend to be local, it's rare to coherently update the entire field, which is what you might need to do if there's some sort of well-defined topological structure. And so Markov chains of this form tend to get stuck also in topological sectors. And this has been investigated carefully, for example, in QCD in this paper, whereas we can see as the lattice spacing is taken towards 0, this measurement of the cost required to generate an independent sample, also known as autocorrelation time, diverges somehow consistently with exponential, even for topological quantities that we'd like to measure. And so, of course, this is a significant obstacle to taking the continuum limit, so to the left on this plot, because the cost is diverging. And so, especially in the case of exponentially diverging costs, which is empirically consistent with topological freezing, it's necessary then to invest exponentially more computational time to get the same statistics. And since the continuum limit is, of course, necessary to remove any sort of systematic effects, at least extrapolating to it is necessary, the closer we can get in our data points, so the closer we can get in terms of the actual calculations we do, the less that systematic error is. And so this is a significant obstruction, essentially, to modern day calculations, and one that improving ensemble generation seeks to solve. Now, on a completely different side of the calculation flow chart, essentially, when we go to actually compute observables, we often run into a different problem, which is that the statistical signal-to-noise ratio of measurements of this sample mean, this expectation value that I wrote down before of any operator O, typically is very small, and therefore it requires a large ensemble to actually precisely estimate many such observables. So the signal-to-noise ratio can be quite simply defined as this should have absolute value bars, I guess, around it, but the magnitude of the expectation value divided by the standard error. And in order to combat a large variance, fundamentally in whatever operator you're measuring, one has to fight this signal-to-noise, or really boost it by sampling more and more samples for a more and more noisy observable. And going back to the previous point, drawing more samples is more expensive and essentially dominates the cost. So this is not just kind of a hypothetical. I mean, this happens in practice for even the most basic 2-point correlation functions that I just previously showed. And in particular, it can be shown to be consistent with exponential decay at large times, at large separation in imaginary time. But unfortunately, that's also a limit in which we get access to these lowest lying energy states without excited state contamination, So really, typically one is forced to find the intermediate ground between the statistical error blowing up and excited state contamination still playing a role. Ideally, you look for some sort of intermediate plateau, but that doesn't always exist. And this can also therefore introduce systematic errors in such calculations. And this idea that this signal to noise decays exponentially actually has been shown generically. And it's quite easy to show just by looking at the structure of the operator that we're considering. So if we think of two-point functions as being written as this pair of creation and annihilation operators, the variance goes somehow as O dagger. And shuffling around where these operators appear to be time ordered, we get that this looks like the creation of some state with 0 quantum numbers and then the annihilation of some state with 0 quantum numbers. At least when fermions are not involved, that story gets slightly modified with the presence of fermions. But generically, regardless of fermions or no, this falls off according to some mass that really is a physical state in the theory. And once you identify what this mass is, you can figure out what the exponential scale is with which the signal to noise vanishes. So just to point out one particular example, for a nucleon correlation function, which corresponds to at time 0 creating 2 up quarks and a down quark, and at time t annihilating them. So this, of course, at large t should fall off as e to the minus mass of the nucleon times time, just based on that spectral decomposition from before. But the variance looks like nucleon creation dagger, which is, in other words, an annihilation operator at time 0, and same thing at time t, modulo the fact that these fermions are playing a role. And so in actuality, though it looks like it should be something with 0 quantum numbers or vacuum quantum numbers, we have to keep the fact that these fermions propagate from left to right. And so the thing that has the lowest energy that this variance correlator overlaps onto is really a 3 pion state. So where the 3 antiquarks pair up with the 3 quarks and form this 3 pion state. But one can show that generically, 3/2 the mass of the pion is a smaller number than the mass of the nucleon. And so the variance is falling off exponentially more slowly, or the standard error is falling off exponentially more slowly than the signal. So if we could resolve both of these problems, since they both provide obstructions to standard calculations, this would be a significant boost to the efficiency and therefore reduce both systematic and statistical errors on the QCD theory results, giving us better access to new physics. So this is essentially kind of the motivation behind seeking machine learning techniques. The motivation is not necessarily to go particularly to machine learning per se, but to find ways to improve efficiencies of lattice calculations in novel ways. But it's worthwhile to note that the structure of these lattice calculations is very much parallel to other data-based approaches in theoretical physics. So what I've just described is that lattice methods in general involve the sampling of many configurations, and then out of this large data set, analyzing the data to extract physics, whether by 2-point correlation functions or 3-point correlation functions or other related approaches. And this then has application in both lattice QCD and, of course, also condensed matter theory. But this is not isolated in the world of theoretical physics. Such kind of large data analyses also appear, for example, when studying string vacua. Certain studies have shown that there's on the order of 10 to this very large number, 272,000 flux vacua. And out of that, one aims to understand something about the structure to find vacuum configurations which mimic the real world and also satisfy some string consistency conditions. So this is a large data problem. And similarly, in the world of many-body quantum states, just one particular example of something that we might be interested in is taking an ensemble of state measurements and doing quantum tomography to reconstruct some underlying states. So then you have a large data set of measurements, and from that somehow you want to abstract and find a useful approximation, a useful generalization of the measurements that you've taken in terms of some quantum state representation. And of course, there are several other applications in theoretical physics that really are data-based approaches. It's not just a purely analytic calculation. And it's sort of worthwhile then to note that there's a structure to these data-based theoretical physics calculations. And the structure mirrors essentially what we see in the world of machine learning. So on the side of generating data, whether it be in Lattice or these other areas, the idea is that the data is drawn from a specific physical distribution. So there's something driving this distribution that we'd like to reproduce. Sometimes the data would need to satisfy certain symmetries, but also very importantly, we're typically interested in low dimensional subspaces of the full configuration space as being the typical data to generate. So for example, in lattice field theory, most configurations in the phase space of the field configurations have very, very low weights and should essentially never appear in an ensemble. On the side of analyzing data, the idea, at least in broad, is to extract general physical properties from some specific ensemble of data. And of course, as we go, it's also important to quantify the theoretical errors. So comparing this picture to the world of machine learning, there's a few differences, but there's quite a lot of similarities. So in machine learning, data generation is a hot topic. And the idea is to reproduce data from some empirical distribution. So say you have a collection of images of faces that empirically defines a distribution of what images, should be more or less likely. And you'd like to reproduce and generate more data from that distribution. And again, this is a world in which there's a low dimensional subspace of importance. So most images are not likely faces in this example of phase dual image generation. It's a very, very low dimensional submanifold, essentially, of all possible images that one could produce that you're actually looking to produce with some likelihood. And in the world of analyzing data, again, there's this structure of extracting general human-friendly, in this case, not physical, properties from specific data. So for example, one might be interested in taking this collection of pixels, which represents an image, passing it through some machine learning tools, and coming out with some classification, which is a human interpretable, low dimensional output that gives you some bulk information about an ensemble of
I have a question.
Yeah.
So does one know whether, for example, in this example that you have here, the set of images that form faces in the space of all images, does it even form a manifold?
Yeah, so maybe manifold is not the right word to use. I think it wouldn't necessarily, because it's not clear that it's always locally going to be, say, homeomorphic to Rn if we want to be very precise.
What do you need?
So in this case, I think it would be fair to say it's just a low volume subspace of the total space of images. So
set
maybe,
of measure zero.
Yeah, that's probably the right way to say it. It's a set of measure zero within the space of all possible images.
And it doesn't have to be connected. It doesn't have to have any topological properties, nice topological properties.
Yeah, I mean, not that I've really thought hard about this problem of faces, but I wouldn't expect it to necessarily have nice properties. Now, on the other hand, maybe one could say something more about the structure of the subspace in the physical case, especially in a lattice field theory. And that would be an interesting question, but not one that I have personally investigated.
Thanks.
Okay, so this parallel between data-based theoretical physics and machine learning really motivates using machine learning to make progress in data-based theoretical physics. Now, before I dive into my particular approaches to doing this, let me just give a one-slide overview of what machine learning actually is so that we are all talking the same language. And roughly, I would say it breaks up into essentially the combination of neural networks, or possibly deep neural networks, and gradient-based optimization. And neural networks, this is a huge buzzword, of course, but really the idea is quite simple. It's just the composition of linear transformations parameterized by some weights with element-wise nonlinear functions. So here I've drawn it sort of already in a lattice configuration. In a general application, it may not be the case, but this is also what you would use often in image applications where you have structure to your data. In this case, the linear transformation really looks like some kind of linear combination of a local patch of input variables to produce the next patch of output variables. And the element-wise function is just something that acts per site or per pixel in the image case. And once we compose several of these, depending on the structure of the architecture you're interested in, you could compose more or fewer. A deep neural network is just a neural net with many such layers. Then we pull out some outputs. And the reason these have gained such importance is essentially that there are theorems that show that these are universal function approximators. So when the internal layers are allowed to be arbitrarily high dimensional, then these are steadily able to encode more and more possible functions. In our applications, because we're interested in this lattice structure, typically, we'll work with what are known as convolutional neural networks. So these weights matrices, rather than being arbitrary linear combinations per output site, it's essentially the convolution of some kernel, that's the name, with the input lattice. So the weights giving this, say, 3x3 linear combination to give this pixel are the same as the weights giving the 3x3 linear combination elsewhere in the lattice to give an output pixel also translated elsewhere on the lattice. So there are fewer parameters in these sorts of networks. Translational symmetry is somehow baked in, but they're very effective essentially at working with these grid-like data. Finally, it's worth noting that these weights are the tunable parameters. So by tuning the weights, that's how one can essentially attempt to approximate a given function between the input and the output. And often I'll denote in this, at points I'll denote that these set of weights overall by omega being just the vector of numbers that should be optimized or modified to attempt to converge towards some target. And in the general world of machine learning, this is done via gradient-based optimization, the idea being that if I define some scalar, what is known as a loss function, essentially giving a measure of how well this net neural network is performing, then by taking a gradient of each component of every W with respect to that measure, we can define a direction in which to perturb these values. And by repeatedly applying such gradient descent, one can converge towards good function approximations. Okay, so all of that aside, there's essentially in there.
Sorry, may I ask a question? Yeah. So if you, yeah, right. So what is the difference between a neural network and an Icing model with, let us say, dynamical, couplings? Like if I have Jij, Sij, and my Jij are also, subjected to some dynamics. Yeah, what's the difference? Is it some kind of sophisticated version of Icing model of this kind?
Yeah, so I guess maybe to consider a slightly simpler case, if we have an Icing model but with non-homogeneous coupling, so there's just a fixed Jij giving the couplings between every pair of sites, that would be like one of these convolution operations in some sense, giving the energy function as the output. I would say the difference is, so if I'm thinking about those as being dynamic, there's some sort of, I guess, integration or summation over those coupling constants. Whereas here, the idea is not to either arbitrarily fix or integrate over the choices of weights, but rather to optimize and find a good choice of weights based on some goal. So I would say the use is different, the objective is different, if that makes sense.
So there is some function that you want to optimize.
Exactly.
Okay, right.
Right, so as shown, this is just kind of a tool, right? This is something that gives a map from inputs to output, and depending on the weights, the map changes. But the way it's usually implemented is this map, the weights are optimized such that the function from input to output reproduces what you would like it to be. For example, identification of features in an image, or classification of an image into different labels. those are all potential functions that you might want from an input, which is an image, to an output. And depending on what your application is, you define some sort of target loss function or metric of suitability, use gradient-based optimization to find the right weights such that that is minimized.
Sorry, so can you say again, what is gradient? Okay, so first of all, okay, I understand a bit what neural networks are. What is deep? Deep neural networks means what?
Deep just means a sequence of many such layers. So I can, of course, compose this many times over, this operation of a linear and nonlinear transformation. So deep is really rather just a broad and vague term saying there are many layers by some metric. It doesn't have a specific meaning really, but
okay,
of order tens to 100, say.
I see. Okay, thank you. And the gradient based, what does it mean?
And gradient based here means, so for a given set of weights, this defines some map from input to output. And this map may reproduce what I want it to, or it may not. So to understand how well that map reproduces a function I'm interested in, one usually defines a loss function. The reason I haven't dropped it on here is I didn't want to go into too much detail about the mechanics of this, but the idea being you define some scalar function that says, how close is this to the function we're trying to approximate? And so that's some number that's, say, defined to be small when this is a close approximation. And it's also something which we can take a gradient with respect to in terms of each of these weights. So I can say if I perturb every one of the weights contains in this matrix, what is the effect on the loss? And by defining that gradient, we can say there's a certain direction in which if I perturb all these weights, the loss is reduced the most. And so just repeatedly taking steps along the gradient means the function is being optimized to reproduce the target function that we're interested in. The neural network is being optimized to reproduce that target function.
Okay, thank you. Thanks a lot.
Thanks, no problem. Okay, so but these are somehow details, I guess, of the machine learning tools. But what I would say is the important point is that machine learning provides us this black box function approximator. And no more essentially needs to be said for the remainder of this talk, because that black box function approximator, without thinking too hard about it, is sufficient to make progress in certain areas of lattice field theory. So the first such area, I guess I should say, I'll just highlight two particular applications that are completely independent. The first is based on these, what are known as flow-based generative models. And the idea is to tackle this problem of critical slowing down and generating ensembles of field configurations. And the second that I'll get to shortly is using contour deformations to reduce this signal-to-noise problem, or in other words, improve the signal-to-noise. And I'll say more about what I mean by contour deformation shortly, but let me first touch upon these generative models. So I should say this is in collaboration with quite a number of people across a wide variety of institutions. So thanks to all of them for their great collaboration. And many of these papers were written with various sets of the folks shown here. So what is the general idea of these flow-based models? Well, I said previously that critical slowing down comes from these local Markov chain updates that have a diffusive nature. So the proposal is instead to do away with these local perturbative kind of Markov chain updates and replace them with just directly drawing samples from generative machine learning models. So if we could, for example, do the same thing as what is shown here for image generation, where you just ask the model for a sample and it produces something where it has high likelihood to produce configurations that you're mostly interested in, then that would be great, except there's a few caveats. One is that these, in order to keep hold of the physical exactness of a lattice calculation, it's important that we actually sample according to this e to the minus action over z. So that exactness of sampling is necessary, whereas a machine learning model may only do something approximately. So that's something that we have to tackle when thinking about applying machine learning here. The other is that the data hierarchy is inverted from the usual situation. So usually in machine learning, you have ideally a very large ensemble or training set of data, and the actual number of degrees of freedom per sample are often quite small. So for example, people, at least early on, would train on, say, 32 by 32 images, and there might be tens of thousands of these images. So there's at least kind of order one parity between these numbers. But for a lattice calculation, especially lattice field theory in 4D, the number of configurations could be quite, degrees of freedom in a configuration could be quite large, on the order of 10 to the 9 or 10 to the 10, whereas typically one only produces on the order of 10 to the 3 configurations. So it's not a lot of samples for a large number of degrees of freedom. And that's something that also needs to be addressed. But of course, there are advantages, of course, to also working in the physical regime, namely that the target probability density is known. So unlike in the case of the facial generation, where, you couldn't write down a probability density as a function of the pixels, it's an empirical distribution. But in the lattice case, it's an analytic distribution. And finally, we also know something about symmetries, which tells us something about deformations or directions in which we modify the configuration and should get something with equal likelihood. And that's something that we can actually gain a lot of efficiency by baking in directly into the models that produce these samples. So based on these caveats, we choose what are known as flow-based models. And the idea is that these models, which have also been applied to images, they produce every sample with a computable probability density. So they're constructed in such a way that you can draw samples, but you also at the same time get the probability density of each sample. So the model knows the probability with which it drew each sample. And that's useful for exactness because one can make corrections based on these numbers. And it's also useful for training, as it turns out.
So why are there, excuse me?
Yeah.
Yeah, so why are there a lot less configurations as compared to degree of freedom?
So this is just a property of
lattice field theory.
Yeah, this is a property of lattice field theory, essentially, that we don't have the computational resources as much as we'd like to generate 10 to the 9 or 10 to the 10 configurations. And simply by looking at, say, the dimensions of state-of-the-art lattices, they have quite a large number of degrees of freedom per lattice configuration.
Okay.
And I have a little question about that. If you go to the large n limit of one of these typical lattice things, let's say, pure gauge theory, then we have good reasons to believe that there's a single configuration which will reproduce all correlation functions, right?
Right.
So then you don't really need large number of configurations.
Yeah, so in fact, this is sort of a point that I hope to touch upon later, but so in the large n limit, that is certainly true. And even in the large volume limit, this is true in the sense that different spatially separated regions of the lattice should be independent just based on the fact that there's a finite correlation length. And yet the physics should be local. And so really, we should be training on some local property. We should be using these translation invariant convolutional neural nets, essentially. And so by having a larger volume, you just essentially effectively have more samples. So this is a bit of a lie. I think while it's true that there's an inverted data hierarchy, we have to use the fact also that we know that it's not that the whole lattice somehow contains only one sample's worth of information. I mean, it contains many different subsamples that all inform us as to what we should do. And the same thing happens in the large n case. In the large n, I mean, each of your matrices is large, and so you have effectively meant a lot of information, even locally, in such a lattice. So yes, I think that's a good point, and we can take advantage.
I would go further and say that if you are genuinely interested in statistical properties of sets which are of low measure in the universe of all sets, or universe that you're looking at, then you should necessarily have this property, if your sampling is right.
Right. Certainly you should have the property that you gain a lot of information from few samples. I don't know that one sample is always going to be enough outside of the complete large N limit, but this is a good point. Yeah, I mean, you're working in a submanifold, and so you gain quite a large information about that submanifold from accurate sampling of the space. Okay, so unless there are further questions, let me plow forward and give a few details then on this flow-based sampling approach. So as mentioned previously, we start with convolutional neural networks, and just think of them as black box function approximators that enact some local function on a lattice. So the fact that it's convolutional just means it's a local function that applies the same everywhere, regardless of the base site X that we're looking at. And to actually construct a flow-based sampler, the fundamental piece, the fundamental building block is what is known as a coupling layer in the literature. And the idea is this is an invertible transformation. So somehow by taking a black box function that is not necessarily invertible, but structuring it in such a coupling layer, one can produce an invertible transformation. And the way this works is much like, for the experts in the audience, it's much like how HMC produces invertible trajectories. It involves splitting the degrees of freedom in half, working with one subset that will not be updated, but using it to produce parameters for the update of the other subset, and then gluing those together. So to invert this, because this top half was not transformed, it's still available in the output configuration. We can still run it through some sort of function to produce the parameters for an inverse transformation of the bottom path. Now that's quite schematic, and I don't unfortunately have the time to go into much details, but the idea is that this piece, this black box function approximator, this neural network, lives inside this coupling layer in a very precise location, such that the coupling layer has several interesting additional properties that the neural net by itself didn't have, but retains in some sense the expressivity afforded by using a neural net inside as a potentially complicated function. Now, this provides an invertible transformation with a tractable Jacobian, and the reason this is important is we can then define what is known as a flow model or a flow-based model by a process of composition of coupling layers. So such a flow-based model involves starting with some simple distribution, which is easily sampled and known. And an example of such a distribution would be just unit norm Gaussian. This produces some sample, which we then pass through several coupling layers, each of which has this structure, has some neural net black box inside it, and has a tractable Jacobian factor. And that's important because this process, being an invertible transformation, effectively defines some squishing and stretching of the space of samples, but one in which the net kind of increase and decrease of probability density is described by a product of these Jacobian factors. So one has a formula that gives the output probability density as a function of the original sample density and the product of these Jacobian factors, which are locally performing some squishing and stretching. Given this probability density and the ability to sample efficiently from such a model, one can measure what is known as the Kullback-Leibler or KL divergence. It is essentially just a way to, as mentioned previously, assign some scalar quantity to how close this distribution is to the target distribution. And that's something that one can take gradients of and can optimize all of these parameters baked into the model such that the output distribution is made to match as closely as possible to the target distribution. So this training process is much like the usual picture of machine learning, but we've packaged in the model all these neural nets in a very careful place so that the whole model satisfies some additional properties like being able to know the probability density and being able to sample efficiently from the model. And finally, of course, at the end of the day, you aren't necessarily going to be able to reproduce your target distribution exactly with such a model, but because the probability density from the model is known, it's always possible to correct this approximation and make such a sampling procedure unbiased by reweighting, for example, by, excuse me, I lost book 4 by accident. Sorry, but by reweighting, for example, by the ratio of the target probability to the model probability density, or a variety of other resampling approaches are also applicable.
So question.
Yeah.
So to measure the KL divergence, you still need sampling from the target distribution, right? So how does that happen? That was the hard problem.
Yeah, so in this case, we choose the KL divergence in the opposite orientation so that it only requires sampling from the model. But yes, in principle, you're right that measuring the KL divergence the other way would require target samples, and that is a hard problem. So we've chosen to sidestep it by working with this opposite orientation.
Okay.
Okay. So for the sake of time, I'm not going to delve into this too much, but the idea is exactly what I just mentioned, that this flow function can be defined by composition of these coupling layers. No more needs to be said. And I will also skip this example.
Sorry, just to ask, so the target distribution in case of the lattice field theory is exponential of minus beta h. Is that the target distribution?
Exactly, yeah. And in the case of a lattice field theory, it would be exponential of minus action. But exactly the same idea.
Right, okay.
Okay, so this essentially gives us a way to define and train a model that we can effectively sample from. And I haven't described it in detail, but that sampling procedure can also be made exact and unbiased. So all it comes down to then is a question of efficiency. Did we define a model that efficiently, closely approximates the target distribution or not? And along the way, we found that it's useful to bake symmetries into the models to improve the efficiency. Now, lattice gauge theory actions typically satisfy many such symmetries, but a few important ones are discrete translational symmetries of the lattice, hypercubic symmetries involving rotations and reflections of the lattice, and gauge symmetries whereby the gauge field is changed based on this local set of parameters. And we focused on the translational and gauge symmetries and baking those into the model.
So one more question. So there's nothing special about a neural network here. So you could try to put any push forward there and try to optimize it. It's just that this is the one that's easy to optimize or something.
Yeah. So in principle, these coupling layers and this composition could be any invertible function. You're right. The advantage of working with coupling layers is just that you're able to systematically increase the expressivity of this transformation. And you can just use all of these gradient-based optimization tools, as you said. Yes.
Thanks.
But of course, if you had another way to define a large expressive family of invertible transformations, then you would be okay to use that instead.
Okay, thanks.
No problem.
And so these phi j's here are the degrees of freedom. So there are
in
10 raised to 10 of them, or
in this picture.
So yeah. So if I'm trying to do a lattice field theory with this, what will be the range of j like?
Yes, yeah. So phi here is just meant to represent any generic lattice field. So for example, if this is a scalar field, then phi j would run over 1 through the number of lattice sites. And same thing for the transformed field f of phi.
So if I'm just naively doing it, this will be these 10 raised to 8 or 9 or whatever DOF that you said.
Yes, and so this is actually exactly why these coupling layers are defined to have a tractable Jacobian. So the idea being, yes, if you were to just directly compute this determinant, it would be horribly large. However, actually, it would be useful maybe for me to show this example. In general, the way these transformations are defined is something where this neural net produces a set of local parameters that do just local transformations. And an example of this for scalar fields might be an affine transformation. And so this is then, it has an upper triangular Jacobian. And so we can compute the determinant of that very efficiently. So there's no order volume squared calculation. Yeah. Okay, so thanks for all the questions. If there's no more questions, then I'll just continue forward with the symmetries aspect. So far we've defined a model that in principle one could sample from. that we can optimize, and that if it's efficient, will give us a very useful alternative to Markov chain, diffusive Markov chain Monte Carlo methods. But one key property of making these models efficient is to bake symmetries into these models. So the idea being that whatever this approximate distribution is, here I'm using the notation U. Again, we're thinking about gauge fields rather than this generic phi. But Q of U, the model distribution, could have these exact symmetries, so these flat directions that correspond to symmetry transformations. Or we could leave it generic and we can simply learn the symmetry by this optimization procedure. But what we found is baking these symmetries in exactly, especially in the case of discrete translational symmetries and gauge symmetries, is very important for the efficiency of training and then the efficiency of the final results. So it turns out that to make a symmetric model, it's sufficient to make this prior distribution where you originally got your samples from before doing this invertible transform invariant under the symmetry, and to make this invertible transformation just equivariant. So a transformation of the input is equivalent to that same transformation applied to the output. And if these two properties are satisfied, then the distribution, one can simply show the distribution is symmetric under the symmetry operation. So if we achieve this and bake the symmetry in principle, the data complexity of training and the model parameter count are reduced, and often this seems to make the loss landscape easier as well. So in the sake, for the goal of translational equivariance, so if we're focusing in on this invertible transform and focusing on translational symmetry, this can be achieved very directly by using these convolutional neural networks that I mentioned. The idea being that inside this coupling layer, these parameters that perform some local transformation of one half of the field, they transform with as an appropriate scalar field under translations, just as the input to this convolutional network transforms. So convolutional neural networks are exactly the equivariant structure that one looks for in this case. And as long as this pattern of division has some residual translational symmetry, so for example, a checkerboard pattern, then you gain that residual translational equivariance in such a coupling layer. So a translation, at least modulo the Z2 breaking, commutes through this layer. Now you can do the same thing for gauge symmetries, and this was sort of at the heart of our recent work on lattice gauge theories, but I think I'm quite late on time, so I'll skip a lot of the details here and just say by careful construction, we can make also these coupling layers equivariant to gauge transforms so that they commute. The application of these transformations commutes with a gauge transform. And the details of that are a little bit involved, but at the end of the day are sort of technical details of the implementation. Now, I mentioned this callback Leibler divergence. And again, for the sake of time, I'll skip the details, but if anyone's curious, I can go back and answer questions about this as well. So the bird's eye view then of this approach is essentially that by parameterizing these flows as the composition of coupling layers, each of which contains these arbitrary neural nets, as just one possible way of parameterizing an invertible transform, we can then perform the standard machine learning loop of draw samples from the model, in this case, because it's a model-based sampling procedure, compute this loss function, this KL divergence, and apply gradient descent to all of the parameters baked into each of these coupling layers to make the output distribution approximate as closely as possible the target distribution, which is just that e to the minus action. Once some desired accuracy is achieved, this is something that you can simply save and keep and generate models from whenever you need. One possible way of making these exact is actually plugging these back into some kind of Markov chain construction, or you can use reweighting, or you can use resampling. There's a number of approaches here. But with just sort of one plot, I want to highlight the results that we've achieved. So applying this in a U1 gauge theory, which does experience topological freezing in 2 dimensions, this was already sufficient. This model with gauge equivariance and translational equivariance was already sufficient to make significant reductions in the autocorrelation time of the topological charge, which again was some measure of the cost of how many steps it requires to get an independent sample. by on the order of 4 orders of magnitude for the largest coupling parameters that we used. So this did show quite a bit of promise and make significant impact in the U1 case. And a similar result was achieved in SUN. So there's quite a lot of detail here, but the important point is this effective sample size over 2 different gauge groups and a range of couplings remains consistently high, and 100% essentially corresponds to a perfect approximation of the target distribution. So the lowest we achieved was roughly a 50% approximation of the target distribution in this highest coupling SU3 case. So quite an effective result in the 2D case. And despite the fact that these were performed in these low dimensions, there's no theoretical obstacle to scaling to the 4D case, which has, of course, phenomenological relevance. So that's something that we're interested in trying in the future. Okay, so I think I have not enough time at all to talk about the second case, since I should really wrap up. So I'm going to defer this one entirely because it is just another case study of applications of machine learning. And I'd be happy to give a summary of this if anyone's interested at the end of the talk. So let me then skip forward to the conclusions. Essentially, taking away the now one case study that we've seen, these machine learning methods already show some promise in the case of lattice field theory. In the case of ensemble generation, we saw that in 1+1D gauge theories, topological freezing can be circumvented, and the statistical exactness is not compromised. In particular, we're also able to get significant efficiency in these models by baking in certain symmetries. And in the case of observables, I had no time to show the results there, but I just want to point out that it's a very similar structure in that it involves deforming the manifold rather than this sort of squishing and stretching within a given manifold. But a similar kind of invertible transform with efficiently computable Jacobian is required and uses machine learning techniques in a similar way to achieve significant reduction in the noise of observables. So there are several future steps in these directions. Ideally, we generalize to 4D. We'd also like to incorporate fermion fields, which has been done already for ensemble generation, but not for these contour deformations for noisy observables. And it might be interesting to apply full machine learning approaches to the noisy observables case, wherein we actually didn't end up using these heavy-duty neural networks. As we were chatting about earlier, I mean, it doesn't have to be a neural network when we're talking about particular optimizable transforms, and it wasn't the case that we used it in that. But it may be interesting to study replacing certain features of this deformation approach with full heavy-duty machine learning tools. So the takeaways then, more general, are that these exactness can often be encoded in physical applications, and to do so requires kind of a use of the analytic knowledge. In our case, we've used the knowledge of e⁻⁻ action as the target distribution for exactness in the sampling. On the contour deformation side, this exactness ends up coming down to just an application of Cauchy's theorem that says I can deform a holomorphic integral without changing its integrated value. And to achieve sufficient properties in the machine learning tools that these analytic exactness guarantees are held requires essentially putting these black box machine learning components inside larger models. And of course, it doesn't have to be a neural network. It could be any optimizable function approximator, but these happen to be efficient and easily optimized, and is essentially then a useful application of machine learning even towards these theoretical physics applications. And of course, symmetries are important throughout physics and especially seem to be important in improving efficiency in these sorts of models. So using the ideas of equivariance, also not included in this talk, but mentioned in these papers, one can use symmetry group averaging to achieve similar effects, then these can be baked in exactly. So just as a parting thought, it seems likely that many areas of these data-based theoretical physics fields could stand to gain from further applications of machine learning, but of course we have to keep in mind this idea that exactness should be preserved, often symmetry should be preserved, and this requires potentially some specialized applications of existing machine learning tools, and therefore there's a lot of interesting sort of development to be done as the field is still young to figure out how that can be applied in a wide range of areas. So thank you for your attention, and I'd be happy to take any more questions that you have.
Yeah, questions, anybody? Yeah, Rishi, yeah, go ahead, please.
So I had one question that this transformation you're making to get the target probability distribution, eventually you want to calculate something like an expectation value of some operator or products of operators. And if the transformation changes the operators in a very complicated way that you get a very non-local or quite non-trivial final operator, then sort of you push the problem into a different problem now. Is that correct, or is there a way to get around this?
So you're talking about this deformation approach, right?
Yes, no, not the contour deformation. Even when you gave the example of the where you change, you use neural nets to get a target distribution. You've gotten the distribution, but now if you want to calculate the expectation value of some operator, if the operator gets really complicated, then haven't you just changed the nature of the difficulty?
So yeah, so if we were to measure operators by sampling this prior distribution and measuring the transformed operators pulled back through F, then potentially, yes, it could be quite complicated. But the way we've approached this problem so far is to draw samples of configurations and push them forward to output samples according to approximately the correct distribution, which can then be corrected and made exact. And so there's no difference in how you measure operators in this. It's still configurations drawn ultimately according to the same distribution that you would have done with Markov chain Monte Carlo. So it's just a replacement for that Markov chain Monte Carlo, but the measurement step is completely the same.
Okay, thanks.
No problem.
Yeah, any further questions?
This gradient descent that you apply on variables, I missed how the number of those variables you're doing descent on scales with the.
So you cut off towards the end there.
How does the number of variables that you apply a gradient descent on scale with the lattice size? The number of
yes. So the number of variables is just the number of free parameters inside all of these coupling layers taken together. So the scaling really depends on, do you increase the number of coupling layers as the volume grows? You don't have to, and possibly you don't want to. And the other question is, do you increase the number of parameters inside each of these, inside each of these black boxes? Do you increase the number of parameters here as the lattice spacings, as the volume scales?
Yeah, that was the question.
I mean, this is something that you're free to do, and it's something that I think without further study, we don't know yet what a good scaling would be. So what we found is that
good results you showed, what did you do?
So to get the results we showed, we kept the architecture fixed. So there was no scaling, but this also didn't involve scaling of the lattice, number of lattice sites. It was only a scaling of the coupling.
So if you go to the bigger lattices, then it may not work.
So in the bigger lattices, if you keep the architecture the same, we're pretty sure that the scaling will be, would not be very effective. But of course, what you'd really want to do is have some sort of scaling commensurate with the scaling of the number of lattice sites. What's unclear is, do you scale that by increasing the number of coupling layers? Do you scale that by increasing the number of layers inside each of these neural nets? Or do you scale that by increasing, say, just the number of weights inside a given layer? There's all of these dimensions that you can scale in, and really without an empirical study of the scaling with lattice sites in each of these three axes, we actually can't say too much yet about the scaling. But I think what one can say is if you work at fixed physical volume, so say we think about increasing the number of lattice sites, but then also decreasing the lattice spacing while holding the physical volume fixed, then there's some regard in which the correlation length is the same with respect to the total lattice volume. And so potentially you could expect good scaling by working with hierarchical methods of some sort. So something where you construct these large scale fluctuations first using the same architecture you did at a coarser lattice spacing, but then you add layers just in proportion to the lattice spacing so that you can perform these refined transformations at the lowest level layers. So it's something we'd like to explore further, but unfortunately I don't have any numerical results on that yet.
You know, ask one question about the architecture. So each layer is a convolution on the previous layer. So they're all it's uniform in that.
Meaning inside each of these neural networks. Yes. So the lattice spacing is kept. Number of lattice sites is kept the same. So yes, this is just uniformly the same lattice geometry of the convolution. What is different though is the intermediate hidden layers may have multiple layers. So it may be a stack of several different lattices inside. And the convolution in principle can act taking this 3x3 box of, let me actually go back by one, taking this 3x3 box of lattice sites, but also across all the layers and using that to define an output at any given step.
Oh, so it's allowed to it's allowed to look at layers, not just the adjacent layer, but also layers beyond.
So what I've called here H is just what would be labeled as one layer, but it's a stack, I guess, of 4 components within one layer.
Okay.
So of course you could also add additional convolution operations, and that would be more layers to your neural network. But yes, yeah, within a stack, it can look at any of these components.
And each of these layers is of roughly the same size as the lattice. So
yes. So this geometry is the same as the lattice, and the number of components is some small number on the order of maybe 8, 16, something like this.
Yeah. And the convolution window is also some constant.
Yes. I believe for the gauge theory results, we use 3x3.
Okay. I don't see any further questions.
So this.
Okay. Oh, I see. Yeah. Go ahead, please.
In a way, this seems to be a bit like a multi-grid algorithm. Do you have any? Did you explore that in any way?
So multi-grid in the sense of this hierarchical sampling where you freeze a coarse lattice and you subsample the fine lattice?
Yeah, that's right. That's how you're getting the large scale. That's how you're capturing the large scale dynamics, right?
So, right, I guess if we go to implement these coupling layers in terms of a hierarchical structure, then I think it would be quite analogous to that. Although the difference, of course, is that rather than being some Markov chain sequential updates, the idea here would be to take a set of noise samples, to take a lattice sample from, say, some noisy distribution, like a pure Gaussian, independent on each site, and build in those correlations just with one pass. But with a hierarchical structure, it would look a lot like one of these multi-grid update schemes. But I should say, I mean, in the current results, we haven't investigated these more complicated architectures. It really is just involving these convolutions locally at the scale of the lattice spacing at each step. And so what we find happens, in fact, is since we use as a prior distribution, essentially this uniform independent distribution over all links, so that looks a lot like infinitely strong coupling limits where nothing sees anything else. Everything's independently sampled. Then as we flow through these layers of the flow-based sampler, we find that correlations get built in just by sequential applications of coupling layers so that things get smoother and smoother, and they approach this, they approach a reasonable looking distribution of correlations which matches the target by the end of the flow, at least for a trained flow.
Okay.
Thanks.
All right. So I don't see any other questions. So let's thanks Tej for this very nice talk. So I'll just tap everybody.
Thank you.
Thank you very